This group of videos is going to cover constant acceleration. Now, calling it that downplays a little bit the importance in that this is really when we get to our final model of kinematics. This is going to be the most constant model that we use in that you're going to see it the most frequently. So this is actually going to be a very long sequence of videos since we get into a lot of meat in terms of deriving some equations, and these are going to be equations that you use a lot. So we're going to talk a little bit about the motion that can actually be modeled as constant acceleration, which again is going to be one of the most frequent, most common things that we see in this class. And we're going to be, again, deriving some of these equations and the plots that go with them. And I can't stress enough how this relates to the learning outcomes, that there's a lot of representations that occur here. There's a lot of plots that you need to be able to recognize and interpret and create yourself, as well as motion diagrams. And the problem-solving aspect here is also huge. That the reason I go through the derivation of the equations is not because I think that it's good for you, per se, to use them, or that you actually would need to ever do that derivation on your own. But this process of starting with one or two pieces of information that we know and getting to another piece of information that therefore must be true based on the mathematically logical process we followed, that's the whole point of problem solving. So the derivations that I'm including in this section are really meant to be examples of the calculation component of problem solving. But remember that problem solving itself is a much larger focus on choosing a good model, doing visual representation, actually doing the math and checking your answer. So a lot of the calculation work in these videos relates to problem solving. So first, graphically, let's just talk a little bit about what constant acceleration looks like. So the first thing to notice here is that this is a plot of velocity versus time. Now, we have two cars here. We have a Porsche, so a fast car, and a Volkswagen, which is perceived to be not a very fast car. So notice that they're both starting at its initial velocity, initial speed of 0. So they're starting from rest at t equals 0. And we would say that they are accelerating with a constant acceleration. Now, remember that when we talked about velocity, we said that velocity was just a change in position or a displacement over time. Well, similarly, if I want to talk about an average acceleration, that is just my change in velocity over a change in time. Now, that by definition would be the average acceleration. Now, note that that sort of equation also looks like a slope, rise over run. But every single point on this line has the same slope because it's a straight line. So if these velocity plots were being very, very curvy, well then we could talk about average acceleration or instantaneous acceleration. But in this case, because they're straight lines, we can actually define a constant acceleration. So this slope down here for the Porsche is actually constant, and the slope we have for the Volkswagen is also constant. And one thing to note here is that, again, how we calculated it was looking at 2 points. So let's first do the Volkswagen. So if we compare the point at 10 seconds and the point at 15 seconds, that's therefore a change in time of 5 seconds, we see that the corresponding change in speed was 10. 10 divided by 5 is 2, and notice that the units here were therefore meters per second divided by seconds. Well, this is just the same thing as saying meters divided by seconds squared, which is how I'll typically write this, and how you'll usually see it in the book. So now if we look instead at our Porsche, and this is a little bit harder to see, but if we take our initial point and this final point here, we have 30, that's not too bad, but now if we drop this down, it's not actually at 5, it's at 6 seconds. So 30 divided by 6 is 5 meters per second. Again, meters per second squared. So when we talk about an object having a greater acceleration, that means that the slope of this velocity line is going to be steeper. It's changing more rapidly. Now, another interpretation we can do here is that you can pick any time you want. For instance, let's pick 5 seconds, and let's look roughly at the speeds of our two objects, our two cars at that point. So they both started from rest. 5 seconds later, our Volkswagen is going 10 meters per second. Our Porsche is going 25 meters per second. So in the same amount of time, the Porsche can get to a higher speed. So we can rearrange an equation like this to say that our change in speed is equal to our acceleration. And since we're talking about constant acceleration, I'm going to drop the average times our change in time. So a larger acceleration will give you a larger change in velocity for the same change in time. So hopefully this makes sense. Again, acceleration is something that we're used to talking about in English. Now, one thing that I want to caution you is that in physics, we rarely talk about deceleration, that when we're talking about acceleration, in this case, we would say these are positive slopes, so it's a positive acceleration. If we had a negative slope, we would talk about that as a negative acceleration. Negative acceleration is not necessarily the same thing as deceleration, just please don't use the word deceleration in here. So now hopefully you've already watched some of the videos that relates position and velocity, and I just want to draw a little bit of a parallel here. That we said the velocity was the time derivative of position, and again s represents a general coordinate, either x or y. Acceleration is in fact going to be the time derivative of velocity. So on the previous slide I showed you that we were talking about the slope, but you could imagine that if we didn't have a constant acceleration, that we would maybe need to take just the time derivative rather than just looking at overall slope. So this is always true. You don't just have to worry about this in terms of a constant acceleration, but even if you had a non-constant acceleration, it is still the time derivative of the velocity. Now before we said for position, if you have some general function, you take the time derivative of that function to then get your velocity as a function of time. Similarly, if we have a time function for velocity, we take the time derivative of that to get our function of acceleration, our acceleration as a function of time. Now what you might notice then is that this is going to mean that our acceleration is in fact going to be the second derivative of position with respect to time. Now where that's going to come in is, for instance, if you have a plot of position, you might remember that second derivative in calculus relates to the concavity, concave up or concave down. So the concavity of your position will tell you about whether you have a positive or a negative acceleration. Only once in a while will we really need to do that analysis in those sorts of terms, but remember that the second derivative of your position is what will give you your acceleration. Now going the other way and thinking about how do you get position from acceleration, that will be in a few slides and will have to be done in fairly great detail. So now we can go somewhat the other way and think about getting velocity or change in velocity from acceleration. And this is analogous to getting displacement or change in position from velocity. So before we said that acceleration was your time derivative of velocity, so change in velocity will be your time integral of acceleration. And again, just like how we could define that relationship that depends on an integral between position and velocity if we have a functional form, similarly, if we have a functional form for acceleration, you can integrate that with respect to time from an initial time to just some general coordinate time to get your velocity as a function of time. So this integration relationship is always true even if acceleration is not constant. Now for the rest of these videos related to acceleration, we will focus on constant acceleration, but there might be a few times in physics where you don't have a constant acceleration, and then you must use this integration relationship.